Hi everyone. The topic for our final group project is object detection on LEGO images. We will start with motivation. What motivates us to do this project is that the world of LEGO has an infinite amount of sets composed of different LEGO pieces. Sometimes, when we see images of these complete LEGO sets on the internet, we wonder what pieces are in these images. It will be useful if there's an automated way of finding out what LEGO pieces are contained in an image of a composite LEGO object. This idea has easily led us to object detection and classification using deep learning methods. In our work, you'll see the implementation of different models like logistic regression, convolutional neural networks, and transfer learning. Also frameworks like ResNet and YOLO. Next, let me tell you about the datasets we're using. The first one is the single LEGO piece dataset, where each data point is an image containing only one single piece of LEGO brick. The whole dataset contains the snapshots of 50 different LEGO pieces shot from a variety of angles. And this dataset is used for our first task. The second dataset is more complicated. It contains snapshots of composite LEGO objects, also shot from different angles. And this dataset is used in our final task of detecting and classifying LEGO pieces in an image. So the method we are approaching this task is that we start with a single LEGO brick classification because we want to know how complex our image data is. The idea is that if we can score high in this task, then we should proceed with detecting and classifying, which is harder. Otherwise, the data is just impossible to learn. In this task, we tried logistic regression as a weak non-deep learning baseline. Then we experimented with deep learning models like simple feed-forward neural networks, convolutional neural networks, and ResNet 18. Here are the results of our experiment on a single LEGO brick classification task. It is clear that deep learning methods outperformed the logistic regression baseline, especially ResNet 18 and CNN. The difference in performance can be attributed to the use of convolutional layers. CNNs are more powerful than other methods in image-related tasks. Here we also give the performance of our models in the test set. Again, as you can see, ResNet 18 has scored the first place.
Okay, so now I'm going to talk about our second main goal of our final projects, which is to use two YOLO models to do object classifications on assembled LEGO models. So as we can see, there's a tiny YOLO version 3 and a YOLO version 3 at the bottom, which we'll refer as the bigger YOLO. So the main difference between the tiny YOLO and the bigger YOLO is that tiny YOLO has much less convolution layers than the bigger YOLO. It has only 24 layers, while the bigger YOLO has around 100 layers with some residual layers. So if you're training larger than 2,000 or 3,000 iterations, then most likely the big YOLO will achieve better results than the tiny YOLO model. But if you're training less than 500 or 1,000 iterations, then maybe the tiny YOLO will achieve better results with a shorter training time than the bigger YOLO. So it really depends on your applications and your usage. So let me show you guys some prediction results on both YOLO models. As we can see in the left picture of the tiny YOLO models, not only did they predict the wrong class label, but also it only predicts like one class. But if you take a look at the left picture of the bigger YOLO, it predicts the class labels correctly and with a reasonable size of bounding box. Now, if you take a look at the right picture of both YOLO models, they actually predict the class label correctly and with the correct locations, but the tiny YOLO ones have a much larger bounding box size than the ground truth label bounding box. So the possible reason is that in bigger YOLO, there's like 3 YOLO layers that could handle multi-scale feature extraction much more efficient and better than the tiny YOLO. So the bounding box errors or the prediction class errors will converge much nicer than tiny YOLO ones. Now let's move on to see the final results after 2,000 iterations of both YOLO models. So IOU here refers to intersection of union, which means the intersection percentage between the prediction bounding box and the ground truth label bounding box. So the higher, the better. As we can see, the big YOLO has a better performance than the tiny YOLO. So speaking about the next steps, we're thinking about maybe collecting more composite Lego pictures with more brick types and different colors. And if time permits, then maybe we'll try different methods such as mass RCN on our dataset.